Hello everyone. Today I'm going to teach chapter 9, Flow over Immersed Bodies, and this is going to be the last teaching class. Next class I will talk about the exam and also solving some example question which help you to review these chapters and also be ready for the final exam. So as I mentioned before, chapter 9 is not is part of the exam but as a bonus question, and also you have to be happy because that's a simple chapter and we are not going to cover the whole chapter, which is mostly about the boundary layers, and it's mostly about the things that we are going to teach in or talk about that in this chapter is mostly about the drag force and drag and lift, the coefficients, and also how to calculate drag and lift. So today, at first, I'm teaching the material and concept, and then solve two questions for you. And this would be very easy question in the exam, very similar to what we are going to teach and solve the example questions. About the final exam, as you know, this is going to be from whole chapters, the whole book that till now we covered, plus the midterm, but mostly the questions come from chapter 4 till the end. So chapter 1, 2, 3 and 7, which is dimensional analysis, we had question in midterm exam. You will have more questions about chapter 4, 5, 8 and 9, so mostly the 9 one is only one question, which is about immersed body, and it's going to be bonus. But the rest of those are chapter 4, 5, and 8, pipe flow. So you will have 4 questions around in these chapters, which you need to follow those things like Bernoulli's, that is mentioned in chapter 3, and also you need to use the introductions in chapter 1 and also more material that you understand about those in dimensional analysis. You will need these in here in the final exam. So make sure that you review all the chapters, but in the pre-exam class I will mostly talk about the questions in this the 4 in the 4, 5 and 8, solving the question for these chapters. So let's start chapter 9, which is flow over immersed bodies. So first, consider the flow over body to understand aerodynamic effects. When the flow passes over a body, like immersed body means that the flow is completely surrounded by the flow that moving over it is going to have a lift or drag that actually at first, because of having an object in the passing flow, the object affect on the flow and get energy from that, so it's going to be a friction over the flow. And when you analyze the flow, you will have a friction, but the reaction force is going to affect on the body as a drag force. So you have to know that, and also the same action happens for the lift. So that's going to be force on bottom to down, or the downward force on the flow, and the reaction of that is going to be like a lift or upward force to the object. So we are using this option for airplanes by using this effect like lift, and make sure that the lift is much more than the drag. So the drag is going to be bad action sometimes, most of the time, but sometimes not. But you will need to make the lift maximum and drag minimum, especially for the racing cars and stuff. So the general characteristics is that a body immersed in a moving fluid experience a resultant force due to interaction between the fluid and the body. That's what we talked about right now. So that's going to be interaction between fluid and body, that the reaction forces on the body is going to be drag and lift. So In the immersed body, we much more what we care about is the lift and drag, because we are going to you have to know that the thing in the airplane is going to be the lift and drag is what you need to understand and also analyze, not the thing that it happens for the flow. So that's why we have to analyze the interaction between these two to find out what is the lift and drag. So general characteristic is that that's two-dimensional. Absolutely, the drag and lift is normal to each other. So that's going to be two components of the force, and the summation of those going to be the total force. So if that's going to be two direction, absolutely the flow is two-dimensional. And also object should be two-dimensional, because it has to be, we have to care about the size in two direction. Axisymmetric object means that it has to be axisymmetric over the in one of the direction. For example, it could be formed by rotating of their cross section cross-sectional area or shape about the axis of symmetry. That's how we can generate an axisymmetric object. So it could be the object is three-dimensional. For example, a wing is three-dimensional, but it in the one direction is going to be the depth, so it's going to be axisymmetric in one of the direction, and it's going to be repeat of the cross-section area. So mostly you can analyze the flow over that by 2D analysis. And the other thing, that object could be streamlined or blunt. The streamlined means that the edge of the object is very similar, or you design the shape in a way that is similar to the streamline that passes over. For example, if airfoil is type of that, or racing cars. These are the shape of the object is you will design somehow to be more similar to the streamlines. Then less effect would be between the object and the surrounding flow. So less effect on the surrounding. Less effect on the surrounding, it means that less effect on the object. Okay, so then it means that you are trying to make the drag very small compared with the lift. So some of those are blunt object. The blunt object means like parachutes, or buildings that you have more effect. On the surrounding. Okay, so as a body moves through a fluid, two forces develop at the top. That one is from on the stresses. So you have a stress on the body. So it means that you have a shear stress, and also you have normal stress. That the shear one is going to give you a drag force, or maybe component of that give you the drag force. So for example, you have the shear force here in this object, the second figure. So we'll have shear stress all over the body and over the surface of the body. But for example, this one has two components. If the force is the direction of here, then you will have two components of the force because of the shear stress. So it's going not always be a component of shear stress is just summation of those is equal to the drag. Sometimes part of it is going to be part of the lift, but mostly because you have an object like streamlines, it's going to be mostly similar, mostly like in the drag direction. and you have normal stresses due to the pressure effect. But if you find out that what is the normal stresses and you get the force, is not going to be exactly equal to the lift, because it happens that the wall shear stress is going to be part of the positive force in lift that you needed. So, but the shear stress is obvious that you have a shear stress because of the velocity gradient close to the wall and boundary layer that you have there. So we'll talk about that in the first chapter, that you know how to find the tau or shear stress and absolutely the shear force. But what about the normal stress? Why we have this distribution of the pressure all over the body? So if you assume that that's my streamline, the shape or the object, so I make it the object somehow like this. That's going to be, for example, your airfoil. Then you see that you have a curvature here and top. So let's assume that the flow comes in this direction, okay? And you think that you have two elements here, 1 and 2, that comes at the same point, starting with the same points, and reach to the body at the same time. Then these two going to split in two directions. So one of those going to pass over here and reach to the tail, and the other one going to come down and reach to the tail. Okay? That's a rule in aerodynamics, that the elements 1 and 2 that reach to the body going to reach to the tail at the same time. So the time that needs that for these two elements, because it's rotational and you can assume that. So these two, based on the boundary, based on the Bernoulli's equation, so you will have that, okay, static pressure in these two are all atmospheric pressure, and you can assume that Z is not that much different between these two. It means that the 1 over 2 rho V squared or V squared over 2G going to be equal for these two elements, right? And since it's rotational, these two are two streamlines, but you can say that the constant number in Bernoulli's are the same, okay? So we talk about that in chapter 3, that Bernoulli's could be applied in only in one streamline, but if it's irrotational, you can assume that the constant that you have for element 1 between 2 points on one streamline could be the same for all the streamlines as long as the flow is rotational. So we have that assumption here. Then we can say that this streamline's constant is equal to the second streamline or bottom streamline. Then these two elements have the same velocity here, right? If these two have the same velocity, means that you have a direction and comes down there, then you will have two objects with the same energy here. Means that the same energy and the same energy, and these two comes down here at the same time. Okay, so you will that's a rule in the aerodynamics. We are not talking about that here, but just assume that these two elements coming here at the same time, right? Then if these two comes at the same time here, maybe in the time this is going to pass here, but the second one comes there, but at the same time going to reach there. Okay, which one has more length to pass when it's going to be t equal to constant for both of them? If t is constant, then the velocity for v1, that's element 1 and that's element 2. This is going to be 1 and that's going to be v2. Okay, so absolutely the length that needs the element 1 passes, L for 1 is higher than L for 2, right? Then absolutely V1 should be higher than V2. Okay, why? Because these two, the V1 needs to be here, element 1 should be here at the same time that element 2 is reached here. Then the absolute V1 and V2 should be different or scaled by the length that the object going to pass. So V1 is higher than V2, right? Then what will happen? If you apply Bernoulli on these two streamlines, the Z's are equal, right? Then absolutely P1 plus V1 squared over 2G plus Z1 has to be equal to P2 plus V2 squared over 2G plus Z2, right? All that's doing big gamma here, but doesn't matter for now because these are going to constant. So if V1 is higher than V2 and you need these to be equal, as long as the Z's are the same, absolutely P2 should be higher than P1. Then P2 should be higher than P1. That's the reason that you have a higher pressure, a static pressure at the bottom compared with the up. So between these 2 points, absolutely the static pressure should be the same because these two are going to come back in the same point. But on top and bottom, when they're passing over the body, these two make a different pressure distribution over the body. That's why we have a positive normal stress or pressure effect on the body, which gives you the lift force, right? That's why you have a lift force. And tau is absolutely easy because that's because of the shear stress that you have. You have to know that absolutely when you have a pressure gradient, you have a shear stress, then means there you have a loss of energy, right? You cannot apply the Bernoulli over there. But here is the reason: when you have a high velocity, that gives you a amount of lift that is huge or considerable. Then you have to know that the boundary layer over the body is very small. So when the flow goes like very fast, then the boundary layer comes down to very close to the object. But when the velocity of the flow is low, then it's going to be so higher around the surrounding of the object. So we are talking about the lift that matter for us. So that means that the flow is so fast, and then the tau or shear stress will happen, but it's very close to the wall. So you can apply the Bernoulli when you have no shear stress or around the object, but in the uniform flow that you have around it, or you don't have any losses of energy because of the boundary layer. So you can apply this equation and calculate the lift based on the flow that is out of the boundary layer around the object. So that's the way that you can calculate the pressure. So it's a meaning behind that, why you have pressure, normal pressure, and you have wall shear stress at the same time, and you will have lift and drag over the body. But what about the direction? So if that's the upstream flow and the velocity is here most of the time, or you can assume the direction of the u is equal to the direction of the y, x and y, and then the drag is in the direction of the velocity or upstream velocity. That's the upstream velocity. Upstream velocity is the flow before reaching the object. Upstream velocity, and that's going to be the direction of the drag, and lift going to be normal to that. So it's going to be normal to the direction of the upstream velocity. That's the lift, and the drag is going to be in the direction of the upstream velocity. That's all you need to know right now. Okay. For now, let's go and find out how we can calculate it or find the components of that. Okay. So in airplane, or as if you check out the shape of the wings in the airplanes, you will see that if you have an airplane there, let's show it here. So if you have an airplane like this, the angles, the wings have an angle by itself. So it's going to be the objects move in this way, but by itself the wings have an angle. That's going to be your angle of attack, or the angles that needs to be different between the upstream velocity and the object. Why? Because if you assume that you have a flat plate, you can assume the wing is like a flat plate, right? And you have a direction, or in Z it has a depth, like a wing. If it's parallel to the velocity of the upstream velocity, then two elements comes up and reach here, and comes down, reach here, right? If these two passes over one flat plate with the same, with that angle is the same, so these two going to reach here at the same time, but also length of the path that the length of the object that passes by these two elements that started here are the same, right? Then velocity are the same and pressure should be the same. Then you don't have any lift here. But when you have a curvature like an airfoil, that you make it to somehow be less length and high length on top, then you will have the velocity difference and also pressure static or static pressure difference between up and down of the object. And also if you have a flat plate but you make it an angle of attack like alpha here, so you absolutely have alpha here, then this alpha going to be make a difference, because these two, that the objects that you have reach here is not going to be here. One of the objects, these two objects that you are going to element 1 and 2 and compare, one of those going to be here, but the other ones reach here. That's because of the angle of attack. So you are starting with two objects that are very close. So one of those going to be here, but the other one, because of the angle of attack, going to be there. Then even though that this is a flat plate, two elements start points are different. Then this one going to pass longer length than the below one. That's why you will have a drag and also the lift. But you have to know that when the velocity is going to be a flat plate, and you will have, that's going to be like a blunt object, you will have a wake here, and that wake by itself give you drag. So that's why the flat plate is not using for the wings, but airfoils are that comes from different tests to find out what is the length or the shape of the airfoil. And you have to know that the airfoils, the shape of airfoils for different airplanes or the jets or in military, these all comes from a huge amount of experimental studies. That's why all of those have a unique ID after finding that what is the optimum shape of the airfoil, and no one going to share that with you, because that's going to be reaching the specific shape for airfoil is expensive for time, expensive for money, and expensive for the stuff that you need to design that of the airfoil. So if you check out in the Google, you will find that there is an ID. So the object has like a length like this one is going to be the C, which is the chord of the airfoil, and you will have the thickness of that, and also the curvature by itself as a function. Then these all comes from experimental study on the wind tunnel with different velocities, and they will find out how this airfoil would be work optimum for the different situation of the airfoil that the airplane is moving on the floor, on the air. So this is going to be also very hard to find out what is the airfoil, the size, and the character or geometrical characteristics. But right now you're not talking about that, because that's not your job to find out what is the lift on a real airplane. Okay, but that's come also from experimental study, and you will have most of the simplification here. So if you have what would be your approach to find out what is the drag or the force, is going to be hard for you to find what is the real drag and lift forces. But because the drag and lift depends to the velocity, so we can normalize like a Reynolds number, which is non-dimensional and constant number or non-dimensional term. Then the drag and lift coefficient also are non-dimensionalized. Okay, so this is going to be drag coefficient. and this is going to be your lift coefficient, which is normalized by 1 over 2 rho v squared a. It's a dynamic pressure, and u is upstream velocity. The A is the area, could be known as also known as wet area or characteristic area or frontal area. These are also the names for that. And rho is the density of the flow or air or whatever the flow is that the body is immersed over that. So density of the flow. So as long as that you have the drag coefficient and lift coefficient for an object, then based on the area that the object has, means that the scale of the airfoil. So for example, the airfoil that you have in a scale 1, and you change the scale to higher scale, then your A is going to change, right? Then absolutely the drag force and lift force going to change because the area are going to change. Also velocity is part of that. So you have to know that the drag and lift are dependent to the dynamic pressure times or area times velocity squared, and the density then is going to scale by that. But the drag and lift coefficients are constant for an object. As long as that you have the drag coefficient, you can use this equation to find out what is the real lift and the drag on a situation that the flow has, so like velocity and the size of the object by itself. So for example, how you can find the frontal area here, if you have a cylinder like that and the flow passes over it, then D times L, D is the diameter of that. It's going to be your frontal area if you check it out from the u velocity. So if you see from this view, then this is going to be your D, and that's your L, right? But if you have that cylinder standing like this in front of you, then the frontal area going to be pi r squared or pi d squared over 4. That's the frontal area. For a like a wing in the airplane, then velocity, and it has a c, which is the chord, and also it has a L. So this is going to be your, because the thickness is not much high, that's going to be your frontal area. Again, because the airfoil has angle by itself. So the flow comes here, then L times C is type of the, it shows that what is the area. So finding the wet area or fronting area depends to the angle of attack and different things in characteristic in the object. So most of the time in the question will give you, or the object by itself has a very simple shape that you can find out by, like cylinder, you can find out what is the area, frontal area. So for a given object, the flow characteristic depends on the size, orientation, absolutely the angle, speed of fluid properties, and speed and fluid properties like rho. Absolutely, because we have rho in the equation, we have u velocity, you have angle, because angle of attack going to give you different frontal area, and because of that you will have a different lift and drag. So these are non-dimensional numbers that could help you to find out what is the drag and lift force could be. So for example, these numbers like u, rho, because fluid property is also here, and LC, which is the length of that, and mu are comes to the Reynolds number, right? So you will give a non-dimensionalized number in that Reynolds number, instead of having the drag, absolute drag and lift coefficients are by itself in non-dimensional number that helps you to find out what is the lift and drag. But Reynolds also brings some of the combination of some of these terms inside of it that also be helpful. And Froude number is going to be again type of the a non-dimensional number that will help you to find the force and drag. Okay, but there are scales for these two numbers. For example, L, for most of the objects that you know or familiar with, or you are going to be see around yourself in the airplane, real airplane, or whatever is around you, the L or length of the wings are from in the object. Like it could be smaller as a fin, and medium size of the turbines, and also long size like the airplane wings. So it's going to be from 0.01 meter to 10 meters in size. Then U velocity is going to be smaller than, very small in 0.01 to around 100 meter per second. That's the range for these two. Then the Reynolds number is in the range of 10 to 10 to the power of 9. That's the range for these numbers. So if you find out, for example, in any question, you find out the Reynolds number based on the velocity that you found, or you did a calculation analysis and find out the Reynolds number in 10 to the power of 12, you will find out somehow that you made a mistake. So you need to know what is in general, what is the range for these, right? So it's going to be helpful. But how you can find out the real drag force and coefficient? For example, in simple shape like a smooth cylinder or smooth sphere, that's a very popular plot that most of the books has it. These all comes from experimental studies on the smooth cylinder and smooth sphere. Absolutely, cylinder needs to know what is the direction or versus the flow, and I think that this one comes from the cylinder like this way over the velocity. So that's the way that it shows this result of the drag coefficient. So for the drag coefficient, absolutely you will have another plot for the lift coefficient. But for now, if you find out what is the Reynolds number over the smooth sphere, right, then you can bring the Reynolds number and read the drag coefficient over that, because Reynolds number is non-dimensionalized. So the diameter of a sphere or cylinder is part of it. Then you will find out what is this. You bring the scale and the velocity of the flow inside of that. Then you don't need to be worried that what is the scale, because you have a Reynolds number. Reynolds have the information for the scale of the object because of the characteristic length and also velocity of the flow, and also rho and u, which is the fluid characteristics, right? That's why we have these two plots for symmetric object like smooth sphere or cylinder, but we don't have that for airfoil, because airfoil could be alpha or angle of attack is part of it, because you know that if the airfoil is that depends to the alpha, you will have a different drag and lift coefficients, right? So that could be a plot in 3D, because you have to know that angle of attack. What is the angle of attack? So you have the Reynolds number, you will find out what is the drag, but based on only one alpha. You can have this plot, but when alpha changes, because this is going to give you different drag coefficient, this plot going to change, right? But for now in this class, as long as that you have a drag force, or you want to know what is the drag force, you can find out what is the Reynolds number and find out what is the drag coefficient. Most of the time in this class, you have simple shapes, right? I will talk about that in two examples now. Okay, so example 1, finding the drag force over a smooth object like a bar. A pitcher throws a 2.9-inch diameter baseball with a speed of 95 miles per hour, and it asks you that find out what is the drag force on the baseball. Okay, so first you can assume that this is not a complete question, so I have to complete it by my information, right? So first, it has to show that is a smooth sphere or not. That's an input in the question. assume this smooth sphere. Okay, so that's the first one. Okay, and use for example, the figure that I showed you. The second one is nu of the air. Nu of the air is 1.57 times 10 to the power of minus 4 feet square per second. That's the second thing that you need. And rho of the air should be 2.38 times 10 to the power of minus 3 slug per feet to the power of 3, or feet cube. Okay, that's the thing that you as an input to that. Okay, then here I will show you that the velocity of the air, because the picture shows the ball in this direction, right? But you can say that the baseball is by itself is a constant or steady, stationary, and the flow passes over, right? So that's going to be my velocity or upstream velocity. Then this object that is stationary here going to affect on the flow with the F1 velocity. Then the reaction of that is going to affect the object in this direction, right? This force is going to be your drag force, and you have to find it out. What is that? Okay, this is easy to show by on the force body diagram. You make sure that this time in this type of question, that for example the acceleration is 0, then you have to show what is the you have to show on this force body diagram. But here you don't need that much, because you only need to show that the drag force, where is the drag force direction, right? That's the only thing that you need. But if you assume that the object passes in this direction, right, then the upstream velocity could be in this direction, because the flow passes here and the object goes in this way, then the flow comes on it in this way, then the drag force is going to be on the other direction. Okay, that's a different thing that maybe happens in the different question, but you have to show it the direction of the force by itself. Okay, so what should I do for first part? At first I have to find out what is the Reynolds number, right? That's the first thing that you have to find. The Reynolds is going to be UD over nu, which is the equation for Reynolds number. So velocity times the characteristic length over or rho over mu or nu by itself is going to be your equation for Reynolds number. Okay, so velocity here is 95 mile per hour, right? Mile per hour. You have to change it to feet per second, right? So I will multiply that by 5,280. This is going to be given in the exam if we need it. So feet per mile and times by 1 hour over 3,600 seconds, which is 1 hour. Then multiply by the d, which is 2.9 inches. We make it over 12 to have a feet, right? Then we don't write it. We don't need that to write it down, but this is only feet, right? And the denominator, you will have nu, which is given and is 1.57 times 10 to the power of minus 4 feet square over second, right? So feet, then the velocity by itself, velocity is going to be, if you do the calculation, is going to be u is equal to 139.3 feet per second. If you multiply feet per second by feet, you have feet square over second, and this is going to be cancelled out by the units of nu. Then Reynolds number is going to be non-dimensionalized. Then the answer of that is also 1.15 times 10 to the power of 5, which is in the range. Okay, so what's next? In the next part, you have to know what is the drag force for it, right? So let's go back to the plot. What is you find out the Reynolds number is 2 times 10 to the power of 5, right? If that's 10 to the power of 5, if that's 10 to the power of 5 here, then 2 times of that is going to be something around here. And if you read that, it's going to be exactly there, which is half. Okay, that's the way you can find the drag force, the drag coefficient. So the drag coefficient using that table or plot, you can also Google that. You can find out what is that. If you don't have the book, it's going to be given if we need it, or we can give you the drag coefficient. As long as that you know how to read it, which is easy. You find out the Reynolds number, and then based on the Reynolds number, you will find out what is the estimation of the drag coefficient. When you have the drag coefficient, so by reading from plot for the Reynolds number that we have, the drag coefficient is almost half, right? So what would be the drag force? It asks you to find the drag force, right? So the drag force has an equation which is that D is equal to 1 over 2 rho u squared times area times the drag coefficient. Okay, so the D is going to be 1 over 2. Rho is given as 2.38 times 10 to the power of minus 3 slug per feet cube times velocity. We found it out that is 139.3 feet per second, and we have the area, that the frontal area for a sphere is going to be the area of the cross section or circle of that. So a circle is actually be seen by the flow, so it's pi over 4 d squared, which d is 2.9 over 12 feet square. Okay, and what about the drag coefficient? We find that that is half. So I will write it down here that d is 1 over 2, that's your rho, that's your u squared, and you need to make sure to have squared here, u squared, and that's going to be your frontal area, and that's feet. Okay, and then by calculating using calculator, then d is going to be pounds. That's a very simple question for finding drag over a smooth sphere in the using the drag coefficient plot versus the Reynolds number. So the second question, in this question is for a racing car. Absolutely, you don't have a plot, and you will not going to find it out in the Google or any book, because the racing cars are highly different in shape, and the frontal area and the velocities are going to be different, the powers are different. So the drag coefficient is specific for the each car. Then you will not going to have any plot to read that for. Okay, so that's why this question is given as an input for different cars. Okay, that's not the different car, it's only two different situations that car could go through it. So the first one is the aerodynamic drag on a car. So it depends to the shape of the car, and you have to know that if you are in a car and then you bring the window down and you drive with the same velocity, the drag coefficient is going to increase because you have more weight because of the open window, and then you will have more drag on the car. Then your power or the consumption of the fuel going to be increased. So the drag coefficient are optimized only for the closed windows, and the shape of those are based on the closed windows, but they will calculate that somehow to make when the window is down or open the window, you will have less amount of the drag coefficient. So here you will have the aerodynamic drag on a car that depends to the shape of the car, and also by itself is if the car window or roof are open, this factor change to the drag coefficient. So it's given that for the first case is windows are closed and the second one is open, and you see that the drag coefficient for the open one is higher than the drag coefficient of the closed one, because in that one you have the shape of the car is more similar to the streamlines. And it asks you that the car is traveling with a speed of 65 miles per hour in both of situations. So the velocity of the car in the first one, when the roof and windows are closed, is going to be 65 mile per hour. So we'll write it down here as a C or UC, which is the velocity for the closed one, and C shows that's closed. The closed one is here, so doesn't matter, so I'll write it down as an input. So U for the closed one is 65 mile per hour, right? It asks you that find out what is the velocity of the car in the second one when the power that is used by the car, or the power that used by the car, are the same. So it asks you what is the velocity in the open one, and O means open. So what is constant here? Absolute velocity or difference. So when the drag coefficient in the open one is higher, then means that you have higher drag force, and if you have the same amount of power from engine, then absolutely you have less velocity for the car. But you have to assume that the velocity are the constant for each of these situations. I ask you that find what is the velocity in the open one. So first you have to assume that F the engine, it has to be equal to F dot the drag, or force, drag force. Why? Because you don't have any acceleration. That's the force balance. What is the second one? The second one is that power is constant, right? Power is constant in both of the situations. Only velocity changes, and it has to be changes because you have the same power and different force balance. Okay, so it asks you, it mentioned that the power in the closed one are equal to the power of engine in the open one. So don't push the gas more to increase your velocity. You will keep that, but only you change the situation of the force balance on the car. Then if the closed one power is the same as open one or open roof, then FC times UC. FC means that the force from the drag and the engine, or the force balance, it has to be times the velocity of the C, it has to be F of the O times the velocity of the O, right? That's the velocity of the open one and force of the open one, and that's the closed one, right? So FC is the engine force, and the balance of the force shows that this is going to be your drag force on the open one. I can show that by D, that's better because you have one subscription here. So D of the closed one times velocity of the closed one, it has to be equal to the drag for the open one times velocity of the open one, right? You can replace the drags with the equation that you have. So 1/2 rho U of the closed square over A of the car frontal area times the CD for the closed one. That's the drag coefficient. So this is going to be your drag force times velocity of the closed one, and you can replace the the other force or the drag force in open one with the same. So rho of the open, u of the open square times a of the car, and cd of the open times velocity of the open. Okay, so you can cancel out 1 over 2, and the flow is the same, so rho's are constant, or the similar, you can cancel out. And it mentioned in the question that assume the frontal area of the car remains the same with the open windows open and roof open, or the one that is closed. So the air frontal area are the same. So what we left is CD in the closed one times U closed to the power of 3 equal to CD of the open one times the U open to the power of 3. Okay? So the rest of that is going to be simple calculation to find out what is the velocity equation. So you have to find out what is the velocity in the open one, and it has to be equal to velocity of the closed one to the power of 3 times CDC closed one over CD of the open to the power of 1 over 3. And then U of the open, it has to be equal to 65 mile per hour, because you can bring it out and get the integral, or get the multiply the power in the 1 over 3, and you will have U of the closed times CD of the closed over CD of the open to the power of 1 over 3. Then 65 mile per hour times the drag coefficient for the closed one, which is 0.36 over 0.45, which is the drag coefficient in the open one, to the power of 1 over 3. Then when doing calculation, you will find out the U is going to be, velocity for the open one is going to be 60 miles per hour. Come back to the first part. What was the question? It shows that you have a car and you fix the power usage of the engine, right? And it's going to give you different force balance, because of the drag force is different when the roof and the window is open or is closed. Then we ask you that if those are closed and you use the same power, then you have the same force balance, right? You have a force balance on the car when this is closed, and based on the drag coefficient that's given, the velocity is also given as 65 miles per hour. But when you bring the windows down and open the roof, then the drag coefficient is going to be changed to a higher number. So what would be the velocity after that? You did the calculation as the summation of the force times velocity, the power, is equal to the power, right? So velocity in the closed one times the drag force that you have in the closed one, multiplication, it has to be equal to the drag force times velocity in the open one. And based on these two and the assumption for the same fluid properties and also the frontal area, you will find out what is the velocity in the open one. That's it. I guess that the question in the exam would be similar to that, and would be as easy as something that you see here. So no worry about it. You have to do the force balance and use the equations to find out what is the velocity, or what is the lift and force, and use the other forces that applied on the object to find out what is your the asked part of the question. That's it. It's going to be simple, and you have to be happy that this chapter comes as an additional topic and is coming as a bonus question. I hope you enjoy the class. So next class I will solve example question for chapter 4, 5 and 8. And these are the main chapters that are going to be covered in the exam with the questions. Have a good one.